In this video, I will discuss Chapter 4, Motions in Space. So far, we've discussed motions of objects. However, we restricted the discussion only to straight line motion. However, straight line motion is not necessarily the standard motion that objects and bodies undergo. The general type of motion that is observed in nature is a combination of straight line motion and also motion around a circle. And so let's look more closely at circular motion and the quantities that are associated with it. Consider an object with mass m attached to a string, and the free end of the string is being fixed in place, and then the object is in motion. The trajectory of motion will be a circle. Let that circle have a radius r. The object is moving with linear velocity v, and the magnitude of that velocity as the object is going around the circular trajectory remains the same. So if the object was somewhere here along the trajectory, the velocity obviously has a different direction. However, the magnitude remains the same. And so no matter where the object is around the trajectory, the velocity magnitude will be the same. And so this is known as uniform circular motion. In uniform circular motion, the magnitude of the linear velocity of motion of the object is constant. Now let's list several important parameters that are related to uniform circular motion. The velocity of the moving mass is always tangent to the trajectory. So the velocity is tangent to the trajectory at any point during the motion of the object. So the velocity is tangent to the trajectory here, the velocity is tangent to the trajectory here. If the object was here, then the velocity would be tangent here as well. So the direction of velocity changes, the magnitude remains the same, but the velocity is always tangent to the trajectory. So velocity is tangent to the trajectory. The speed of motion remains constant. So speed remains constant. And the fact that this mass is moving around a circular trajectory and not along a straight line means that there must be a non-zero net force acting on this mass. And this is the consequence of Newton's first law. Just as a reminder, Newton's first law, the first part of the statement was about an object that's moving along a straight line with constant velocity. And the object will continue to move like so unless a non-zero net force acts on it. And so this mass constantly changes direction as it's moving around this circle. Therefore, a non-zero net force must be acting on this mass. Again, a non-zero net force acts on the object. This force is called centripetal force. And the reason it is called centripetal force is because it is directed towards the center of this circle. And so at all instances or at all moments of time during the rotation of this object, the centripetal force points towards the center of this circle, and we are going to label the centripetal force with F sub c. So this is very important because the direction in which the force points makes the object to constantly turn around the center of the circle. Constantly, the mass is constantly turning. And so the centripetal force always points towards the center of the circle. So we also know from the second law that if an object is under the action of a non-zero net force, then that object also must be accelerating. Just as a refresher, the second law stated that force is equal to mass times acceleration. So if a force is present and acting on an object, this object must be moving with some acceleration a. So the centripetal force is directed towards the center of the circular trajectory, and we know that the acceleration due to that force is in the same direction as the force. So that means that the acceleration at which this mass is moving must be directed towards the center of the circle as well. And so the acceleration is directed towards the center of the circle, and we are going to call this centripetal acceleration. So AC is centripetal acceleration. So then I can write Newton's second law specifically for uniform circular motion, and that second law will look like so. The centripetal force is equal to the mass of the object times its centripetal acceleration. Now remember also that this mass has linear velocity v that doesn't change in magnitude. So the magnitude of the velocity remains the same. But we know from chapter 2 that the acceleration and velocity are related. And so without doing the derivation, which for this particular concept is beyond the scope of this book, it turns out that the centripetal acceleration is related to that velocity, as the centripetal acceleration AC is equal to the square of the speed of motion divided by the radius of the circular trajectory. And so if I combine the two formulas together and substitute AC in the second law with this expression, I get a different form of the centripetal force, different formula for the centripetal force that allows to do certain calculations. So the centripetal force will be equal to mass times speed to the second power divided by the radius of the circular trajectory. So these three relationships are all relevant for uniform circular motion. Now, depending on the specific situation where the object is undergoing uniform circular motion, different types of forces can play the role of centripetal force. So let's make a quick list of several common forces that can be the centripetal force. So in the example with this mass that is tied with a string and rotates about the free end of the fixed end of the string, the centripetal force is the tension in the string. So tension is one type of force that can be a centripetal force. Now consider the Earth orbiting around the Sun. So the speed of rotation of the Earth around the Sun is constant. So the velocity changes direction, but the magnitude remains the same. And so, therefore, the Earth experiences centripetal force and it rotates around the Sun. This centripetal force is gravitation. So, gravity is another force that can be centripetal force. For a car that is moving, driving down the road and it's taking a turn, if we want the car to stay, let's say, in the middle of the road at all times as it's taking the turn, that means that a certain force must be acting between the tires and the road so that the car is taking this turn without moving left or right. And this force would be static friction force between the tires and the road. Let's sketch this particular situation to make it more visual. So here is the road and a car is taking a turn. So here's the car, this is a top view. And so I want the car to stay in the middle of the road following this dotted line. So that means that the car, as it's taking the turn, cannot be moving this way or that way, only along the dotted line. That means that essentially the car is moving with constant speed along a part of a circle. So that means that there must be a centripetal force that's acting on the car in this direction towards the center of the circle, which is somewhere here. And so the centripetal force will be directed like so. And what is this centripetal force? Well, this is the force of static friction. And so under what condition would this force be lost and the car can get either move to the outside of the road or to the inside or even get off-road? Well, that can happen when the road condition change and let's say dry road becomes wet road or icy road, or if the car starts to actually go faster around the circle here, around the corner, around the turn. In this case, the static friction force will be insufficient to keep the car fixed in the middle of the road, and then the car will slide in either direction or off-road. So these are three examples of specific forces that can play the role of centripetal force. Now let's do one example to illustrate the application of the formula for centripetal force and centripetal acceleration. We have a mass of 30 grams, which is tied to a 70 centimeter long string. The mass rotates at 2 meters per second, finds the centripetal acceleration and centripetal force acting on the mass. So let's list what we know. So we know that the mass is 30 grams, and we know that the length of string is 70 centimeters. So that would be the radius of the circular trajectory that this mass is undergoing. So the radius is 70 centimeters. We also know the speed with which the mass rotates. So V is equal to 2 meters per second. And we want to find the centripetal acceleration and the centripetal force. Okay, so first let's find the centripetal acceleration. The centripetal acceleration is calculated as V squared divided by R. And so this would be 2 meters per second divided by 2 meters per second squared divided by 70 centimeters. Notice that the units for length here and here are not the same, which means that the radius here must be converted in meters before the calculation. So that is 2 meters per second squared divided by 0.7 meters. So that's going to give me 4 meters squared per second squared, divided by 0.7 meters. So the units of meters and the second power here will cancel out. And finally, the result is 5.7 meters per second squared, and the units are, as expected, the units of acceleration. Now let's find the centripetal force. The centripetal force is simply the product of mass and centripetal acceleration. So that is equal to 30 grams times 5.7 meters per second squared. Notice that the mass here is in the wrong units as well. As I said in the previous lecture, the mass, when you're calculating force, always must be converted to kilograms. So 30 grams is 0.03 kilograms times 5.7 meters per second squared is equal to 0.171 newtons. And so this is the centripetal force that acts on this mass as it rotates around this circular trajectory. And with this, I will conclude the lecture on motion in space.